So for our last talk, we have Sam Phippen with us. So let's give him a round of applause.
There's like wires all up in here, and I like wander during my talks, so this might get really exciting. So this talk is What is Processor? I'm going to be talking about abstractions and programming languages and processors and all of that good stuff. To introduce myself, my name is Sam Phippen. I'm Sam Phippen on Twitter, Sam Phippen on GitHub, and everywhere else if you'd like to stay in contact after the conference is over. Yeah. Also, I'm wearing this t-shirt, rather unfortunately, from a company called Test Double. I basically only have conference and company t-shirts left in my wardrobe because I'm that kind of person. And so like people have been asking me if I work for Test Double today, and I just thought I'd disclaim that. But they're nice people, and Justin Searles, who is basically the only person from Test Double anyone's ever heard of, is a really lovely guy. So I'm sorry for like pretend representing your company, but not really. Justin, I love you. So at the end of Carrie's talk, she proposed thinking about how we think about code and thinking about how other people write their code. And she said, you should ask yourself, how would Sam write code? And the answer is like this, just all the time, just screaming constantly, destroying computers. I actually once burned out the keyboard in a MacBook that I owned because I reached the like keyboard cycle press limit after like 4 years, and there was a giant hole in it. So yeah, maybe not program like me. Okay, talk. So I wanted to prefix any of the actual content of this talk with a disclaimer that everything I'm going to say in this talk is what I like to call a convenient lie. Convenient lies are things that we as programmers believe about how the computer works in order to like make it possible for us to get our jobs done without having to understand the details of the billions and billions of components inside our computers that make them work. Convenient lies are things like abstractions on the network and the file system. They enable us to not think about the horrifying like underlying quantum physics that actually drives computers. And so many of the things I'm going to say in this talk like aren't even close to actually true. Instead, they provide us a useful model to reason about how computers work. And so if you know loads about low-level stuff, that's awesome. But this talk is not really meant to provide like deep, powerful, intuitive understandings of all of computer science, but instead intellectually interest you in how to understand how computers execute programs. So let's talk about Ruby. I think most of us are here today because we enjoy programming in the Ruby programming language more than most of the others for the kinds of jobs that we do. Being a Ruby programmer is kind of interesting because of how Ruby lets us think about the code we write. When you write Ruby code, you're typically thinking in terms of the people, the domain, the systems that you're working in. The language that you encode into the computer is similar to the language that you use when talking to non-technical people about how you build your programs. You write expressions like 3.days.ago, not new date time system.current time minus 3 times 24 times 3,600. When I'm working with newer developers, I explain this to them as thinking in terms of the domain. The domain of your application is all of the stuff that your users and your business people believe to be true about the application, and not the details of how it works inside a computer. The domain is things like shopping carts and line items and delivery addresses. It's not things like memory and bytes and the network I/O. The opposite of thinking in terms of the domain is thinking in terms of the computer. This is all of that stuff that I just said, but it's worth noting that for some programmers, their domains actually overlap with how the computer works. If I'm developing a driver for a graphics card, I actually need to be thinking in terms of that low-level stuff like memory and syscalls and so on. And so my domain actually overlaps with how the computer works. For most of us who build web applications in Ruby, though, our domains tend not to be about computers. They tend to be about things in the real world. And this is where Ruby's ability to hide many of the messy details of how computers work from us really comes into its own and enables us to be really, really productive as developers. So I like to think of this as one way that you can measure the abstraction of a programming language or system. If you're writing code in Ruby, you're thinking less about the computer than you would be in a programming language like C, or if you're writing assembly. So let's draw a line and start talking about some different kinds of programming languages and where they might fall in how much they make us think about computers. Well, if we just have Ruby there in the middle, we need another programming language to compare it to. And I think Python is a good candidate. I've got like 80 more slides of this, by the way. Like this, it's all doodles. So just like Ruby, Python is a dynamic interpreted programming language. It has object models, functions. It hides many of the details away from us as well. And when I'm working with Python developers, I tend to find that they also spend most of their time talking in terms of domain concepts, not in terms of computer concepts. So I'm going to put Python at the same place as Ruby on the abstraction line. Now, I know that might be a controversial call at a Ruby conference, and if you fundamentally disagree with like Python and Ruby being in those positions, then like grab me and we can argue over beer later. But like, I think this is a reasonable call for now. So in order to like continue to look at this, we're going to need to move up and down in terms of abstraction. And I'm going to go ahead and argue that the SQL programming language enables us to think less about how computers operate than either Python or Ruby do. The reason for this is that when you express a program in SQL, a query, it looks something like this. You're describing a solution. I'm going to leave it to your imagination what the doodles on the next slides are.
I'm upset.
You won't be, you'll love it, trust me. So when you express a program in SQL, a query, you're framing a problem to the computer and it solves it for you. This is a fundamentally different way of asking the computer to do things than either Python or Ruby. In Ruby, when you write a program, you're expressing a top-down list of instructions to solve some particular problem. You're thinking about like how that program is going to modify the state of the computer in order for you to come to a conclusion. And the order of those operations matters when you're modifying that state. You understand the idea that like the computer has memory and stuff is changing inside it, if not overtly, then on some inner level. With an SQL program, you don't really have any guarantees about the order of execution of any of the parts of it. But that's not important, because again, you're just like expressing to the computer how you want it to solve the problem. You're effectively framing it and letting the computer fill in the blanks. So that's SQL. The next programming language that I'm going to talk about is C, and I think like it's fairly obvious that C is much less abstract than the other programming languages we've been talking about, but I'm by no means saying that it's the direct next level down. I've increased the size of the gap there, and there are hundreds of programming languages that I could put between Ruby and C, but I don't really have time to do an exhaustive list of every single programming language that one could assess. There are a lot of differences between Ruby and C, and I'd like to start by looking at one of them, which is how Ruby programs execute versus how C programs execute in computers. So I think most people who work in Ruby understand that when they write a source program, in order to execute it, they also need a Ruby interpreter. What the Ruby interpreter does is it reads the first line of your program and consumes it. When that line of your program is consumed by the Ruby interpreter, it works out what instructions it's going to need to tell the processor to execute in order to achieve the result that you expect from that line of the program. And so that information gets round-tripped into the processor, and results go back to the interpreter. The interpreter then assesses whether it needs to continue executing and reads the remaining lines of your program before finishing executing. The thing that's important to note here is that you have both human-readable source code and an interpreter present at execution time, and your program can't go without either. These things are coupled in order for you to be able to execute your program. And this is what it means for Ruby to be interpreted. The code that you write as a programmer can't natively run on the processor in your computer, and so the interpreter is needed in order to run a Ruby program. The difference here between Ruby and C is that C is not an interpreted programming language. It's compiled. What it means for the C programming language to be compiled is that when you have a source program, you need to pass it through a compiler, and instead of that... Can I go on? And when the compiler executes, it doesn't actually directly execute that program on the computer, but instead it saves it to what's called a binary file for execution later. The binary file is in the format of instructions that can be sent directly into the processor in your computer, and so if you want to execute that program, that's all you have to provide. Now, it's worth noting here that what that means is that source code is separated from execution time in a compiled language paradigm. And this can be useful because it means that you can distribute your program as a single file as opposed to a collection of source files as is typical with Ruby programs. And this is done, for example, in Go and Rust and a few other programming languages. This difference between compilation and interpretation is interesting because it shows us that programming languages don't all necessarily execute the same way, but it doesn't really talk to why C can be considered to be a low-level programming language. And in order to talk about why people sort of describe C as a low-level programming language, I'm going to need to talk about a computer from history, the PDP-11. Now, I was going to look up exactly how old the PDP-11 computer is, but as I was writing this talk, my dad happened to glance over my shoulder, and he said, "Hey, that's the first computer I ever programmed before you were born." And I was just like, cool, that means it's old enough to not really matter. So the reason the C programming language actually came into being was because of this computer. The PDP-11 had a new feature inside its processor called byte addressable memory. And that byte addressable memory feature hadn't been served by programming languages that existed before the PDP-11 computer. And so some people who were working with it were like, we need to invent a programming language that gives us this feature. Let's go away and do that. And so when you go on to Hacker News and they tell you that the only way to be a real programmer is to learn C because it models the machine, that's simply not true. The processor inside my laptop bears basically no resemblance to the processor inside a PDP-11, apart from some models. And so C models really, really old processors and one particular model of execution that was popular back at the time. The way that the C programming language ends up working on modern computers now is that we have 40 years of learning about how to optimize it. And so modern compilers actually take this C code that models execution on a processor with basically no transistors and turns it into code that can be dispatched onto processors with billions that can do all kinds of fancy, clever things. And so C is not fundamental to programming in any real sense. It models one kind of execution from a long, long time ago that happens to be close to the metal of certain kinds of machine. However, there are other programming languages that much better model modern processors in a similar way, and those aren't fundamental either because it's not only those processors exist. So You might hear that C is fundamental and that you're a bad programmer if you don't know C, but like, I don't really think that's true. One other reason C is kind of a nice idea around low-level programming is to do with how memory works. So in the Ruby programming language, when you access memory, you don't really even realize you're doing it. You make a new object, you work with that object, and then you just stop working with the object, and the memory that's associated with it goes away. It gets garbage collected. Well, C actually wants you to manage memory yourself more or less directly. And the reason for doing that is that on some computers, memory is extremely restrained, and also manually working with memory can often give you much better performance than if you're letting somebody else deal with it for you. And so in C, you actually have to do your own memory allocation, access, and release. And if you've ever actually done programming in C, you'll know that like manually working out how to free all the memory that you allocate is really, really painful, and like garbage collectors are a good thing. So like it's all trade-offs, and C just represents a specific set of trade-offs for like a certain kind of memory model. So that's the C programming language, and we're now going to move further down and talk about assembly. Before I go too far into assembly, I need to explain a concept called registers. A register is a tiny, tiny piece of memory. And the reason that they exist is if you look at the motherboard of your computer, you'll find that like the memory and the processor lie a handful of centimeters away from each other. But a handful of centimeters and like the speed of a modern processor is a really long distance and a really large amount of time. And so instead of the processor having to reach out to memory every time it needs to work with a value, it has these small pieces of memory inside itself called registers in order to be able to work with them. They're small enough and they're fast enough that we can put them basically everywhere on the processor, and they're used to deal with like temporary results as we build our programs. So let's actually look at some assembly code. This is a very, very simple assembly program that I've written. The first thing that you should note is that like this is just like a linear sequence of lines of code. Assembly programs don't really have control flow statements as we think of them in Ruby. There is no if, each, for, while, nothing like that. The way control flow is done in assembly is through other means that are out of the scope of this talk, but interesting if you want to look at them. In an assembly file, each line of the file represents exactly one instruction to the processor. And this instruction is made out of parts. The first part is called the operation. And the operation can be thought of as like the kind of function that you want to execute on the processor. In this file, there are two operations. One is mov, which is really just move. For some reason, people who write assembly programs drop like instructions must be 3 characters, which is weird. And then the other parts are called operands, which can be thought of as the arguments to this function. So here we have a move instruction with the first operand 3 and the second operand $C. Here, $C is being used to denote a reference to a register. And so you can see here in this program, we're accessing 3 registers, C, D, and A. To show you what it looks like when this program executes, here we model 4 registers and the execution of each instruction. So the first instruction executes, and it moves the value 3 into the C register. The second one executes, and it moves the value 4 into the D register. And then the add instruction executes, and it adds together the C and D registers and stores the result in the A register, giving us 7. And so this is like what assembly instructions are. As Steve said in his talk, they do one very specific thing and like allow you to build programs out of those extremely simple building blocks. Now, it's worth noting that the assembly program is still a textual representation. It sits in a file that you could open with your preferred text editor. And because it is in that textual representation, you still need to compile it, and you still execute that compiled binary at a separate time. One thing that's worth noting is that unlike Ruby or C, assembly programs can't be executed on all processors. So when you write a program in Ruby, you have some expectation that like you can execute it on like an ARM system or like a different kind of system, and the same thing is true with C. Assembly programs are specific to a kind of processor, and so I have to write one kind of program if I'm going to be targeting an x86, which is the kind of processor I have in my laptop, and a different if I'm going to be targeting ARM, which is the kind of processor most people have in their phones. So that's assembly, and like the next layer beneath it is the first form we're going to be talking about, which is not a textual representation of programs. Eventually, when your processor executes a program, it needs them as a series of numbers, and we call that series of numbers binaries. These are the results of the compilation that I was talking about earlier. If you look inside a binary file, it's basically just a long string of numbers, and just like the assembly program was made up of instructions, and those instructions are made up of parts, the binary file is the same thing. It's just the instructions have been encoded into an integer representation. So just as before, we have operations and our operands. So let's talk about how this code actually gets executed. And I should just say, this is one model of assembly code execution that is like done in lots of processors, but there are other models that you can use. There are other kinds of processors, and again, this is not a universal truth. The model that I'm going to be discussing today is called fetch, decode, execute, retire, or FDER for short. And this is like what's going to happen inside our processor, and let's go through each step now. So let's start with fetch. The thing about processors is they'd be very, very sad if they just lived on their own. They need other hardware in a system in order to really be able to do anything and like get any results done. And one of the more important components in the execution of programs is main memory. When you take one of those binary files that I was talking about and you load it for execution, the contents of that file gets copied into memory, and each instruction gets given an address. So here we might have a program with 3 instructions starting at address 0 and going through to address 2. When the processor wants to execute it, it needs to fetch the instructions from main memory, and to do that it needs to know where they are. So when that program was loaded into that address, the processor will also have a register, one of those small pieces of memory I was talking about earlier, called a program counter. And the job of the program counter is to tell the processor where in memory to look to fetch the instruction. In this case, address 0. The processor has another register called the instruction register, which is for holding instructions inside the processor. And basically all that's going to happen is we're going to copy this value across. The reason the processor needs a register to do this, as opposed to going out to memory, is like the processor can consume instructions very, very quickly, and memory is slow. So in order to be able to read this as fast as the processor needs, we again need one of those registers to hold the value. And this is all that happens in the fetch step. There's an address, it gets fetched, and loaded back into the processor. The next step is called decode. And the job of the decode step is for the processor to understand the instruction it's just fetched and get ready to execute it. So let's imagine we have an instruction which is going to add 1 and 2 together and put the results in register 3. This gets encoded as a binary number, and that binary number can be broken down into parts. Once the processor's loaded that instruction, it begins breaking down each byte of the binary number. The first one meaning add, the second one meaning value 1, value 2, register 3, and so on. Once the processor has decoded this instruction and understood what each part means, it needs to begin working with various pieces of its internal hardware in order to be able to actually run the program. So let's just zoom in a little bit and add our registers. Again, doodles. So along with the program counter and instruction register, processors typically have other pieces of hardware that are associated with them. In this case, we're going to have a few more registers, which are general purpose pieces of storage. A unit for the processor to deal with memory, what's called an arithmetic logic unit, which performs basically operations on numbers and operations on Boolean values, and an I/O unit. Given that we know that this is an add operation, the processor will activate the arithmetic logic unit, which is the part of it that's actually going to dispatch for execution. And given that we know a result is going to get written back into the C register, the processor will also activate the register C. And this is the end of the decode step. Basically, the processor has loaded the instruction, begun understanding what it is, and activated each of the internal pieces of hardware that it needs in order to be able to execute the instruction. The execute step is where computation actually happens. And let's just clear out the bits of hardware that aren't going to be used, the program counter and instruction registers, and also just generate some space, or left pad. Ashley here is from NPM. So anyway, execution. The processor knows it's adding these values together, and so it taps the values out of the instruction, and it sends all of that into the arithmetic logic unit. The arithmetic logic unit basically performs the computation and produces the result. In our execute step, all that really happens is the pieces of hardware that made ready to perform computation are used, and they have the values routed into them. All of this is happening electronically in like circuits inside the processor, and there's like weird signal stuff happening, but this is what happens at like a high level. The retire step is the final step of execution, and its job is basically to make sure that results end up where they need to be, and prepare for execution of the next instruction. So in this case, we take on result 3 from the arithmetic logic unit, and we write it back into the C register. Once that's happened, we're ready to execute the next instruction, and so the instruction register is zeroed out, and the program counter is incremented. The reason the program counter gets incremented is as follows. So if we look back in memory, we have our program loaded as a series of instructions. Incrementing the program counter basically tells us to get the next address of our instruction, so we're ready to repeat the cycle over and over again. And that's basically how programs get executed inside the machine. I'm definitely lying to you. There are about 1 million details that I left out here, but that seems fine. To quickly summarize, in the fetch-decode-execute retire model, the job of the fetch step is to get the instruction from memory into the processor ready for execution. The decode step gets the processor ready by activating each of the circuits within the processor that are going to be used for the instruction we've just loaded. In the execute step, we actually do the computation the instruction has asked us to do. And in the retire step, we make results available and we clean up. I think this sort of stuff is really interesting, and programmers are like uniquely qualified to understand it, even if it's not going to make us better at like our day-to-day lives. And so I hope that was an enjoyable explanation of how computers work. Thank you very much for listening. Sam Phippen on Twitter, sam@funimplausible.com. This talk is CC BY NC Share Alike licensed, if that's your thing. Cheers.